I will start now with the talk for this morning, the first talk. I have a clock here to check that I will not talk longer than 15 minutes, and I will start. You already have a background in AI from different perspectives, and some of you, of course, know what I'm telling you on this first slide, but nevertheless, that we get a common ground, I want to remind you a little bit about the history of AI. So in general, we say that there are three waves of AI. The first wave, which was the beginning of first broader interest in AI in the 1970s, 80s, was focus on explicit representation of knowledge. In this time, powerful algorithms have been developed with provable characteristics, and we use them today and we teach them today in our AI lectures. They are an important part of the methods we have, but a large amount of human knowledge is implicit. So it's not available to inspection and verbalization. This is called Polanyi's paradox. How is it possible that we humans can know more than we can tell? Yeah, and this is also the bottleneck for knowledge-based AI methods. So the second wave, as you all know, has its focus on data-intensive machine learning. So machine learning research is as old as AI. Yeah, you know that the perceptron algorithm is already has been developed back in the 40s and 50s, and that the first wave of neural networks has been end of the 80s and beginning of the 90s, but the hype we experience now is due to the impressive results of deep learning, of highly data-intensive approaches of machine learning, for instance, for image classification. So the success of machine learning is exactly there where we have the restriction with knowledge-based approaches. Mostly we work there to generate models about mostly implicit perceptual knowledge. For instance, if you want to give a complete description of what a cat is, to recognize a cat on images in every possible situation, this will not be possible. But if you train deep network, let's say a CNN with many images of cats, and you really consider a good sampling strategy that you cover all as many instantiations of possible images of cats as possible, you will get a good model. But here, of course, we also have a problem, a different one. Here we have high demands on the amount and the quality of data, and especially the labeling of training data in specialized domains demands very high expertise, for instance, in medical diagnostics or quality control. And as we already heard in a great talk yesterday, we need to be aware that these machine learning models don't come for free. We have many click workers in the backgrounds who label millions of data, yeah, and so it's an illusion to think that knowledge-based AI is lots of hard work, and for data-intensive AI, you just need to collect randomly some data. This is simply not how it is. So a very nice discussion essay of Kambhampati, a very well-known researcher in the domain of AI planning, in 2021 had the title Polanyi's Revenge. Remember, I told you about Polanyi's paradox, basically the knowledge engineering bottleneck of explicit knowledge-based AI methods. And Kambhampati observed that We experience with deep learning a similar restriction, you could say a data engineering bottleneck. And so he says, what we need to grasp is that we understand when we should apply machine learning approaches and when we should apply knowledge-based approaches. In this paper, he mentions, and we all, I think, have experienced similar things, that in industry currently, sometimes people throw away hard-earned causal knowledge, which they have written down, and throw it away, collect data, learn models which are by far not as precise and as helpful as what they originally already had as a perfectly good knowledge base. So this is, of course, kind of ridiculous. So what we need is the wisdom to know when use knowledge-based methods, when use machine learning, and furthermore, we need to combine both, for instance, in hybrid approaches. And I talked about the problem of labeling. We very often are in need of interactive machine learning approaches. Okay, so the third wave, I should mention this also explicitly, is has been introduced as Explainable AI, XAI. But nowadays, what I already mentioned, hybrid approaches and interactive machine learning are also subsumed under this label. Back in 2016, a small hype within the hype of deep learning started, namely Explainable AI. And this started with a talk at ICHKAI with the following slide, basically, where David Gunning said, well, when we have these black box machine learning approaches, a system might output, well, there is a cat on the image, but we don't get an explanation, either a causal explanation or a justification why. When we would ask a human, why would do you think this is a cat? A human might give you features, understandable, verbalizable features like it has fur, it has whiskers, it has claws. And for things which we cannot explicitly formulate, maybe showing prototypes like, look, and it has ears in the following form. So this hype within the hype at the beginning resulted in many approaches about visualization of relevant features, pixels in this case, in the input images, and people reasoned a little bit naively, well, when we highlight what the system, the learned model is looking at, quote, then people understand what's going on and then they will trust. Of course, this is completely naive and absolutely not how it should be. There is this very well-cited essay of Tim Miller about explainable AI perspective from the social sciences, which I strongly recommend to read if you didn't already know it. So what I already mentioned is furthermore that we should use hybrid approaches. Look at the top figure on the right, where we combine knowledge representation and maybe deductive inference methods from the first wave AI methods with data and inductive learning from the second wave. And we can use learning to adapt our explicit models, and we can use what we already know to inform and constrain machine learning. But what we can do is that we can use explicit knowledge in the form of knowledge representation, but what we can do additionally is use the human in the loop to correct maybe decisions of the system, and we can also use this corrections to adapt a model. This is especially important in domains where we don't have high quality data and where we don't have enough, a big enough sample of representative data. And for these human in the loop approaches, interactive machine learning, therefore, it is especially important that the human understands the reason why an AI system, a learned model, came to a specific decision, because it might be right for the wrong reason, due to overfitting, for instance, or it might be wrong where we see that, for instance, that specific data are not available, have been not available during the learning phase and should be provided later on to adapt the model in the desired direction. So, very often you hear the argument that there is a trade-off between accuracy and interpretability, this is not true in general. So, of course, when we have complex perceptual knowledge, like for image classification problems, it is really not very helpful to try to learn with a linear regression, say, or a decision tree. But on the other hand, we have many data, like tabular data or structured data, where interpretable methods of machine learning are as performant as neural networks, for instance. So here I recommend you the paper of Cynthia Ruddin, Stop Explaining Black Box Machine Learning Models, after you learned the model, right? And use from the beginning interpretable models. So I see the time and I will hurry up and will skip some of the slides which we can use or can refer to in the discussion. I want to point out that already in the 1980s, Donald Mickey, which is the founding father of the AI research in the UK, introduced ultra-strong machine learning as a concept. And he said, weak machine learning means machine learner produces improved predictive performance with increasing amounts of data. There is the focus on predictive accuracy as the only measure of quality of a learned model. Strong machine learning means that the system or the learner additionally requires that the learned hypothesis or model is available in symbolic form, interpretable for humans, making the learned model from a black box to a white box. And finally, ultra-strong machine learning means that the learner, the machine learning system, can teach the hypothesis to a human whose performance is consequently increased to a level beyond that of the human studying the training data alone. And this is exactly, I think, what we want for modern AI applications, that we have joint decision-making possibilities for humans and AI system to collaborate together so that both can profit from the strength of each other, so to say. So what we want is having human AI partnerships. Keeping humans in the loop is not only ethical, for reasons like transparency of decision-making or the appreciation of human labor, but it's also, I hope that I could convince you with this very high-level arguments about this, practical and necessary, because in human AI partnerships, we can provide knowledge to constrain machine learning, and we can correct model decisions for model adaptation. So I will skip examples from various projects we have in this domain and come to the takeaway. Of course, you know the book of Gary Marcus, I think. If not, I again strongly recommend to read this book. third wave AI approaches support human AI partnerships. They provide methods for ethical AI, and adequate explanations and interaction interfaces require interdisciplinary cooperation. I skip the examples. I'm sorry about that. I would have shown you that. And the challenge is that we need to reach this a broad dialogue with all stakeholders for fair and helpful social technical implementations of AI systems. Thanks a lot, and I'm looking forward to your questions and the discussion.
Algorithms, AI, are increasingly used also in public administration and in the public sector. For example, public administration, they look for ways to prevent some unwanted events. So, for example, a person who just lost their job, that this person will stay unemployed for a very long time. Or that children are maltreated in home because their parents can't take care of them. Or in criminal justice, the question, you're probably aware of this example by Angwin and colleagues, whether those who are awaiting trial should be kept in prison or be released. And I will just continue talking. And usually our goal is we want to get an estimate of some risk that some unwanted event will take place, as I said. Somebody stays unemployed for a long time. And the question is, are there side effects that we may not want, so that the risk assessment or the decision that we make based on the risk assessment will harm some societal groups more than others. And against this background, what we want to do here is we want to discuss an approach that we developed for profiling people who just lost their job to get an estimate of the risk that they become long-term unemployed. And this risk score, this estimated risk score, can then be used by people in the job agencies to prioritize cases and allocate welfare state measures accordingly. Now, algorithmic profiling of job seekers is nothing new. It has been used for almost 30 years now. But what we have seen is that for a long time, people didn't seem to ask those questions of fairness, biases, and the like. Only in recent years, when in Austria, the Austrian Public Employment Services discussed or actually developed a system, the AMS algorithm, that they wanted to introduce to their public employment services, became questions related to discrimination, fairness, and bias very apparent. And I think this is related to this hype of AI, ML methods, and also the increasing popularity of asking those questions related to fairness and the like. And so those methods or those approaches have been used for a long time, but questions related to discrimination and fairness have only caught attention very recently. Now, probably I don't need to speak much about that, but there's a risk of bias in algorithmic profiling because we usually use historical data, in our case, historical labor market data, and an algorithmic system can easily learn to reproduce any biases and unfair patterns that are present in that data. And when it comes, for example, to unemployment, you all probably know that unemployment is heavily related to, for example, gender, because women, when they take over family care, they tend to stay out of the labor market for much longer than men, for example. And in the past, women didn't work as much as men. And so there are all these biases that are present in the data, and while a statistical algorithm or a machine learning algorithm is probably very accurate when it picks up all of those associations found in the data, and including the unfair ones, which we probably do not want in our decision model in the end. And so our models can learn to discriminate or make unfair decisions based on those protected attributes, or as we would call them in the social sciences, ascriptive traits: gender, race, religion, and the like. A second explanation is that model performance can be affected by misrepresentation in the data. So, for example, when we have way more people of one group in our data than of another, but this is probably nothing new to you. And so the hope, we want to increase efficiency and effectiveness of government spending by using AI, by using ML algorithms, is easily jeopardized by all those biases that are present in our data. And so we need to investigate them. And Germany actually hasn't used these algorithms at all. And they did discuss it for a long time, but there were always concerns that this could backfire. And given this increase of fair ML research and fairness concerns about such models as in Austria and in other countries, we asked, well, can we develop, based on German administrative labor market data, can we develop such a system? And then what would be fairness implications of typical modeling choices? So how does the question how we classify people based on which thresholds, which policies we use, how does that affect fairness metrics and fairness in general in our prototypical model? Just to give you a very brief info on the data that we use, it's 2% random sample of all people in Germany who are employed subject to social security. That's the majority, excluding civil servants. And we focus on data from 2010 to 2016, which results in some 600,000 unemployment episodes from 300,000 individuals. So an individual can become unemployed for more than one time, obviously. And the outcome is standard for this area: long-term unemployment if somebody stays unemployed for more than 12 months. Could also be 6 months, but typically it's 12 months. And about 15% are actually long-term unemployment. We derive some predictors from the admin data, and we focus on 4 protected groups: so female versus male, non-German versus German, and the interaction of the two, so non-German male and non-German female. And we want to understand how such a model could easily result in unwanted side effects. And with that, I'll turn over to Christoph.
Right, thanks. All right, then when it comes to the model setup or prediction setup, we consider different model types. So of course, we could envision that we could use different methods, different ML methods to build such a system. So we could start with something like logistic regression as a starter, then also look at other approaches, penalized logistic regression, or ensemble approaches, like more ML focused or more ML heavy approaches maybe. And also another question is, what type of data do we use for training, of course? So we could look back of all years that we have at our hands. We could also restrict ourselves to 1 year. And just to be clear here, our test set, so to speak, is data from 2016. So we use those two training sets to build models. Then we could question whether we want to use those protected attributes as features or not. So whether we want to include them in our models or not include them. And then another question is, how do we actually classify them, people as being at risk of LTU? So we use 3 policies here. So a rather straightforward approach would be to essentially use the risk scores that we get out of our prediction models, order them by risk, and then cut off maybe the highest 10% or the highest 25%, and then classify those as being LTU or at risk of long-term unemployment. Another interesting policy is look at those individuals that are in the middle, so that are classified as being at, let's say, medium risk of long-term unemployment. And this is something that has been, let's say, it's inspired by the application in Austria, where they also essentially focused for the most part on those middle risk observations, and were thinking about targeting interventions at those for those folks. All right, so meaning with this setting, we have like a grid of options that we can use for building models. Then we can evaluate those models with respect to different, let's say, ways of considering fairness. Now, kind of specifically in practice, of course, one obvious thing is first, we could look at accuracy or prediction performance, here measured by the F1 score, and say, okay, we're not maybe just interested in the performance overall, but also we're interested in subgroup performance. So how well does our model work for female folks, for non-German, and so on and so forth. So subgroup performance would be one aspect. And then we also look at other measures that are, I guess, common in the FAML literature. So one way approach would be to look at statistical parity, just essentially looking at what is the proportion of non-Germans that are predicted as being long-term unemployed compared to the corresponding proportion for Germans. So it's just a descriptive, let's say, measure of looking at our predictions. And then another approach would be, okay, let's now look at a very specific type of error that we could make. We could make false negatives, and then we could also compare those false negative rates across groups again. So false negative rate for non-Germans compared to false negative rates for Germans. Right, so what do we get? There's no need now to really look into detail here into those figures. So those box laws represent essentially, or each dot here represents one model, or more specifically here, it would be the F1 score, so the performance of one specific model that is built by those different combinations, so model type, features used, and so on and so forth. And we here see now model performance broke down by group. And I guess the most maybe not super surprising takeaway here is that model performance differs by subgroups. So it turns out that if we build such a model, actually those models perform not so well for non-German compared to other compared to the overall performance, for instance. So there seems to be a bit of a performance gap here. Why this is the case? Okay, we can speculate maybe later on, maybe in the discussion. I could also think about, okay, maybe non-Germans are not nicely represented in our training set, so that there can be many things that come into play here. Okay, so prediction performance differs by groups. So there's a gap here in performance across subgroups. Now, what do we also see? We also see that those predictions models actually, they amplify existing differences that we have in our data. So this is looking at statistical parity. And the interesting thing is actually just the comparison between the observed difference in base rates. So how is actually kind of as measured in our data, what is the difference between the long-term unemployment rate between, let's say, non-German and German? This difference is highlighted here with this big red dot. And the other differences here, so the other colors are indicating the statistical parity differences for the trained models. And you see that they are amplifying the true difference. So the true differences are pretty close to like 0 at least. And we see that then depending on the classification threshold, we are amplifying in both directions. So we might amplify such that non-Germans have a higher probability of being classified as LTU or lower, depending on whether which cutoff we actually use. All right. Then also, as I mentioned, we looked at false negative rates. So another way of measuring now concretely maybe fairness issues. And we see actually what's going on here again. We see that for many groups, for non-German males, again, depending on the classification policy, there are quite some differences in the false negative rates. So we make kind of, let's say more errors for non-German when it comes to using policy 1A and B, and less false negative rate errors for non-German when it comes to using policy 2. So again, there's an interaction between the type of classification policy in a sense that we use. And this also to some extent explains what we saw earlier, that we actually make kind of, that we amplify those differences, and we do amplify them because we're making mistakes, actually. All right, We can come to the summary.
Yeah, so what are our main takeaways? Well, developing such a system is not just about developing a very performant algorithm or a very accurate algorithm. There are many design choices that we need to make, and this is probably something where we need to heavily interact with those with the domain knowledge in the field of labor market policy. We need to decide, like, when do we classify someone as being at high risk? Do we focus on those with a medium risk because we think if we support them with our training measures from the labor market agency, then we can actually change their status in the long run? We need to conduct rigorous fairness auditings, and we need to conduct them before systems are put to practice to avoid situations where, well, after bad press, we need to scrap the system right away. The fair ML perspective sheds new light on systems that have been used for a long time. Remember, in the beginning, I said these systems have been used since 1995, 1996, but only in recent years have people started to ask questions. Well, do we need to be concerned, for example, about like fairness, that they treat people differently? And these evaluations need to be put in context, because it's not just about evaluating some popular fairness metrics. We also need to understand what is the underlying allocation principle. So in some situations, differences in who gets support and who doesn't get support based on our algorithmic profiling systems may be well justified. So for example, if you find that women have higher chances to become long-term unemployed, then maybe we want to focus on our support, especially on that group. And that is, for example, codified in the German social labor market code book, that these systems shall be used to remove existing disadvantages for some groups. And then another question is, well, once we have identified those at risk, we still need to assign them to different support measures. And there we can also rely on more causal inspired machine learning systems. Like we could use potential outcomes thinking, for example, to evaluate what would be the expected effect under which treatment, and then choose the best one. However, integrating then the fairness perspective into this causal ML thing is still not very well understood. And so many questions remain. This is just the first take, but we hope that it's interesting for you, and we're happy to answer any questions.
Good morning, everyone, and thanks for being here. I also wish that I was in Germany, but for some teaching reasons, I couldn't be there in person. So as mentioned, I'm a philosopher. So in the previous Q&A for the previous talk, there were lots of interesting questions about what do we mean by fairness and justice in relation to algorithms. So obviously, I'm not going to resolve those questions, but I'm going to kind of add a different perspective that maybe the previous talks touched on later less. And so that's going to be some insights from political philosophy, and in particular, the works of one of my favorite political philosophers, Iris Marion Young, where she criticizes, basically, like she comes from the position of criticizing some metrics for resource allocation as kind of like the only way we can bring in justice issues. And so basically my aim in this 15 minutes talk would be trying to connect that part of political philosophy, which hasn't been related to algorithmic fairness, and hopefully provide a more like broader landscape for the questions we need to go forward with. So before I give my talk, I wanna, obviously my talk is not about social movements, but I'm an Iranian woman, and I would like to take a moment to treasure the memory of many people in Iran who are fighting these days against different kinds of structural injustices. Yeah, that's all I can do from here. All right, so let's start with the talk. We hear quite often that algorithms are socio-technical systems, and they're touching, and by algorithms, I'm going to mainly focus on data-intensive machine learning algorithms, or the second wave of AI, as we heard in the great talk by Ute. And so these algorithms kind of are touching on, are being incorporated in, or informing decision-making in various high-stake decision-making domains. So we have all kinds of examples from using these algorithms in mortgage allocation, in healthcare allocation, in employment, and also in criminal justice system. So because these algorithms, according to different measures, according to different perspectives, and many different kind of investigative journalists, also scientists and etc., have shown some sort of harmful biases or wrongful biases against vulnerable groups, we've seen like a growth of a new field of AI research called algorithmic fairness. So as Ute mentioned earlier, there has been this hype within the AI system, like explainable AI. And so at the beginning, maybe most of the motivations for working on explainable AI has been due to questions about, oh, how should we understand these deep neural networks? Like we have these epistemic limitations, etc. And then some people took explainability to become an ethical principle for making AI ethical, right? So because here we are talking about ethics and AI. So explainability then kind of transformed into becoming an ethical principle for the design of AI systems. Similarly, fairness become a second or a different ethical principle for designing AI systems that can function properly in the society and can benefit humanity. But similar to the question of what do we mean by explanation, we come to the question of what do we mean by fairness. And the notion of fairness very tightly is connected to the notion of justice. So sometimes people use these two notions interchangeably when they want to talk about the moral or political quality of their decisions. They say, okay, we have a fair decision or a just decision. But anyways, that is the importance of these fairness principles for data-intensive machine learning. So then what happens is that there's been this need to talk about fairness, and mathematicians and computer scientists and AI researchers started to kind of mathematically formulate different criteria of fairness, or I will talk about these criteria as criteria of social justice, with the objective of remedying these harmful, like wrongful harms that could result from biased algorithmic outputs by resolving a local resource allocation problem, right? So if you have a data-intensive machine learning algorithm that is supposed to allocate resources fairly to those who are in need of those medical resources, we are really resolving a resource allocation problem. Similarly, if we are using an algorithmic system that is supposed to make decisions about in the criminal justice system in the United States, we have lots of examples of that. Then again, we are resolving a risk allocation problem, and if you take risk to be a kind of a mathematical or computational good, again, we are resolving a resource allocation problem. So if we a little bit kind of zoom out with respect to what we are doing in algorithmic fairness, is that we are mathematically formulate one criteria or another of social justice. Then we kind of like try to incorporate that into the design of the algorithm, and we resolve a local resource allocation problem. And so these metrics are typically rooted in some ideals of local distributive justice. So those computer scientists who talk about philosophy, mainly they talk about John Rawls and other philosophers, mainly coming from the Anglo-American tradition, who have done lots of work on distributive justice. And so in like public media, even John Rawls is known as the most popular political philosopher among AI/machine learning kind of researchers. But the interesting thing is that in political philosophy, there has been philosophers who criticize Rawls because of his limited scope of the conception of justice. And so today I want to kind of like rely on those critics of Rawls in relation to algorithmic fairness and make two claims. So one is that algorithmic fairness, the way we are doing it today alone, cannot easily accommodate the concerns of structural injustice. And I will say shortly what does that mean. By reducing it to local distributive justice. So we have this other dimension of structural injustice that we need to talk about, and computer scientists need to say what do they think about that. And the second claim is that the paradigm of responsible algorithmic fairness maybe is the kind of research paradigm we need to slowly move to instead of just talking about algorithmic fairness. And the reason is that responsible algorithmic fairness, or the notion of responsibility, tries to bring in some structural injustice dimensions into the work on algorithmic fairness. Okay, so first claim is that algorithmic fairness alone cannot easily accommodate the concerns of structural injustice. And I want to start with a thought experiment, with an example. So consider Mandy. She's a low-paid employee and a single mother of 2 underage children, and she lives in a very fast-growing city. And then, as the evidence shows, a notorious tech giant has a vested interest in automating services in various institutions in Mandy's city. And because this tech giant has a presence in the city, it contributes to driving up housing costs locally and makes it very unaffordable for many people to live in their present homes. So one day, Mandy's landlord gives her a notice of eviction and then intends to renovate basically the place, because she says, okay, you need to go out. I want to renovate this place and then I want to rent it later. So given Mandy's limited option, she kind of decides to apply for a bank loan. And the bank loan is kind of like the decisions about the loan allocation from this bank are given according to the algorithmic services that are designed by the tech giant. Okay, so again, this is a thought experiment, just want to bring in the idea out of this. So we have this tech giant is automating everything, including the bank services. And so the tech giant then faces like public pressure. There are lots of grassroots movements, like newspapers, other media writing about this kind of like problem with housing, and especially the fact that many low-paid people are really affected negatively by the presence of tech giant. So what should we do? And tech giant says, hey, we have an ethical team. And so maybe what we can do in our own capacity is to distribute a number of low interest loans to people like Mandy. How should we do the distribution in a fair way? The tech company asked. They have a panel of a hired ethicists, and they propose that the loan allocation algorithm should comply with an, let's say, equality of opportunity fairness metrics. I mean, as one of the speakers mentioned, and like people who ask a question, and I think most of you know, there's so many different metrics, and that itself is a question of how to choose a metric. But let's assume we have contextual justification, or the tech company has contextual justification to go for the equality of opportunity fairness metric. And so Mandy then receives the maximum amount of this loan thanks to this distributive fairness metric in the design of the decision-making algorithm. And so the tech giant says, okay, we made a fair decision here. We kind of allocated this algorithm fairly to Mandy. Now us, let's say as the citizens of the city, would ask whether this algorithmic decision is fair or just. Okay, in order to really answer this question, we need to start from this point that many sociologists and philosophers of science acknowledge, and more recently, more and more machine learning researchers also acknowledge that algorithms are socio-technical entities. So there are lots of recent work emerging in many different AI labs, many different universities, people talking about socio-technical studies, in particular in relation to algorithmic systems, machine learning algorithmic systems. And the idea is that these systems have these social and technical dimensions so inherently tied to each other that we can't just talk about the technical dimensions, or we can't just talk about the social dimensions. We need to reconceptualize many things and try to see how we can perceive of these entities or these data-intensive systems much more clearly in socio-technical terms. So if we take this claim seriously, that algorithms are socio-technical entities, it means that in order to assess an algorithm as fair or just, we need to evaluate the fairness-related algorithmic interventions in the proper relation to the relevant sources of social injustice. So if the algorithmic system is trying to make a fair decision or is trying to get rid of an unjust situation, then the algorithm should really intervene directly or related to the relevant sources of social injustice. But not all sources of social injustice, according to some political philosophers, and you can disagree with, of course, have necessarily resource allocation solutions. Sometimes the injustice is related to the structural problem. Now, there are loads of works that has been done in continental philosophy by French philosophers, German philosophers, within the past, say, at least 100 years, where they particularly wrote about structural injustice. I quote Iris Marion Young, who in her work always relies on those previous works. And so if you want to read more and you search for other references, just write to me. But I think this is a very interesting and great description of what are these structural injustices, and then related to this talk, why they matter to algorithmic decision making. So according to Young, structural injustice exists when we have some social processes that they put large groups of people under systematic threat of domination or deprivation of the means to develop and exercise their capacities. This systematic threat does not necessarily need to be intentional. Sometimes it could just be there. It's just in place. And then there are ways to measure it, and there are ways to talk about it. But at the same time, these processes enable some others to dominate or to have a wide range of opportunities for developing and exercising capacities available to them. And according to Young, structural injustice occurs as a consequence of many individuals and social institutions or legal institutions acting to pursue their particular goals and interests, for the most part, within the limits of accepted rules and norms. Now, going back to the case of Mandy, then just to finish with the first part of the talk, going back to the case of Mandy, there we have the case of structural injustice, meaning that just allocating resources or allocating a high amount of loan does not necessarily resolve her problem, because if that loan is not enough, we have done something, we have allocated resources fairly, but at the end of the day, she cannot resolve her problem. And maybe she even accumulates a mountain of debt, and she ends up at a worse situation at time T2 as compared to when she has received this fair allocation of loan. So acknowledging that not every problem necessarily or easily can be resolved by resource allocation is very important to be acknowledged and to be kind of implemented or thought by AI and machine learning researchers. Now, what should we do with this? Not like, let's assume that you agree or you agree or you accept the first claim that I made, that there are some sources of structural injustice that might not easily have some local redistributive solutions. What should we do? We go back to Iris Marion Young again. She says that maybe we need to incorporate responsibility, the notion of responsibility, in a very special way. I will talk about it briefly, into the research on algorithmic fairness. And if we do that in a proper way, then maybe we would be able to correct for errors in the current implementation of the algorithmic fairness research paradigm. So there are many ways to talk about responsibility, and philosophers many times talk about responsibility when they are talking about responsibility gaps and moral responsibility. But young and political philosophers have a very interesting forward-looking kind of active or action-based conception of responsibility that they call the social connection model. The social connection model is forward-looking. It says what can be done when we go forward. It doesn't necessarily just want to go backward and blame people. So in many contexts, we need to kind of go backward, find who is responsible or who should we blame because for the occurrence of an event, and then do some legal or social action against this entity. The forward-looking model kind of tries to acknowledge that, okay, there are some problems. We don't necessarily need to find who to blame for, or even if we can find who to blame for, there is not one individual, there is a collection, there are generations of people. And this conception of social connection model of responsibility also applies in cases of search for climate justice and other problems. So here I want to talk about it in relation to algorithmic decision-making and just decision-making. So in order to kind of like implement at least at one level, this notion of responsible justice or responsible fairness, we need to think about how we can reduce injustice by reflecting on 4 parameters of reasoning according to Young. So these parameters of reasoning are called power, privilege, interest, and collective ability. Very shortly, I tell you what they are. So in order to assess whether an algorithm is fair or not, we need to talk about or think about the notion of power. So power basically can refer to different levels of causal influence and relevant capacities that contribute to a particular kind of problem. So we need to identify where this power comes from and then how to do with it. Then the conception of privilege, that some people, some institutions have more privilege than others, given certain structures. And maybe these people need to contribute more to resolve the injustice problem because they have this privilege. So people who have power or institutions who have power have more responsibility. People who have privilege have more responsibility. And maybe some people have more interest, maybe because they are affected, or maybe various other kinds of social interests. So, and then the last conception is the notion of collective ability. Some collective organizations have capacities and resources to try to design policies or design many different social solutions in order to kind of go for bringing about a better situation. So basically then going back or tying this concept to the case of Mandy, it means that in the case of Mandy, we cannot just figure out, or this tech-based tech giant can't just try to kind of say, okay, I'm going to automate a particular metric of fairness. This is justification for a choice of this metrics. And then now that's all I can do in order to bring about a better or a more just situation for the life of Mandy. No, maybe in that case, a tech giant needs to take account of the existence of structural injustice, partly because of the presence of this tech giant in the city, and then some work, some creation of new social entities or new programs or policies should be also incorporated in order to make, in order to do something such that the social injustice problem is a little bit resolved. Okay, so what could be the practical consequences of this? When I think, as Ute mentioned, we need to do lots of interdisciplinary work. So,
Atoosa?
Yes.
Sorry to interrupt. I'm just wondering.
It's the last slide.
Yeah, perfect.
Yeah.
Okay, thanks.
Very quickly. Okay, so practical consequences. There are some motivations and justifications for operationalizing relevant local distributive elements of social injustice. They need to be evaluated more carefully. We can't just say because we have these 1 or 2 metrics, then we are having fairness or justice in effect. And then this effectiveness again the effectiveness of these metrics needs to be analyzed in the context of social power. Their intervention mechanisms to secure social injustice should not just be limited to local distribution and fairness metrics, and algorithmic fairness should be treated in relation to responsibility. So if you have more interest to read about this work, this paper was recently published in this proceedings, yeah, I'll be happy to answer any questions. Thanks for your attention.